Hello, and thank you for inviting me to give a talk on the Rain Enhancement Hub. My name's Alan Gadian. I'm a senior scientist at the University of Leeds, National Centre of Atmospheric Science in the UK, and I'm going to talk about marine cloud brightening and enhancement of rainfall and the risks associated. So the first slide I want to show you this. I've divided into three sections: introduction, marine cloud brightening, and then I'm going to talk about coded modulation, which is really quite complex. So I'm going to provide some background initially to say why we need to cool the planet. I think you probably know, a lot of you know this already. I'm going to introduce the concept of marine cloud brightening, which is quite a novel concept. And then I'm going to talk about coded modulation, which is really quite complex, but I want to give it a flavor of what's actually happening. So I'm going to move on to the second slide, and this basically shows the results of measurements for the past 5 million years. And we are in the right-hand section of the right-hand third in the area called the Holocene, that's mankind. And you can see that temperatures have been relatively stable. And then on the far right, you'll see a prediction for 2050 and 2100. So the temperatures will, in fact, be hotter than has ever been in the Holocene while mankind has existed. And it implies there's going to be temperature changes and other meteorological changes, including rainfall. So warnings have been given about the fact that we're in a changing environment. There's an American scientist, Jules Charney, in 1978, basically using analytical models, said we're going to be 4 degrees C warmer. James Lovelock, who was American stroke British, he talked about the revenge of Gaia, and he said that we're going to be in difficult circumstances. And then there was Martin Rees, who's the 15th Astronomer Royal since 1680, and he says mankind has to deal with this new situation. So we've talked about the planet's warming up. There's lots of discussion about why the planet's warming up, and it's quite complicated. But if you look at the planets of Venus and Mars, you realize we're actually in a sweet spot. So I've given 3 complications on this graph. There's quite a lot there's quite a lot on here. The first is that we have to consider water vapor in the air, saturated water vapor. So for every degree Celsius rise in temperature, there's 7% more water vapor in the atmosphere, in the lowest layers. So a 3 degrees rise in temperature will produce a 20%. Now, this fact is largely ignored by many politicians, scientists, but it's the fact that we exist at all is because we're in this sweet spot. So the second point is to examine this water vapor effect. And if you look at the warming due to the surface, 19% or 24% without clouds is due to carbon dioxide, and 50% or 67% is due to water vapor. Thus, a water vapor increase of 2 to 3 degrees is going to be very significant in the warming of the planet. And that's the third point, that the consequences of the water vapor increase are that obviously there's going to be more water in the atmosphere, so there's increased precipitation, severe temperature changes will get worse, dust storms, especially in Africa and Asia, are going to get worse, agricultural production, and there's something called the Atlantic Meridional Overturning Circulation. There's also one in the Pacific, and that will have a significant effect because that will cool. So some of the northern hemisphere will actually cool. So the message is we have to do something in the near future. And the final introductory slide is if you look at the plot in the middle of the page, you will see a curve. Now, this is a difference between the incoming and outgoing radiation. So this just summarizes what is actually happening. Now, on the top left-hand side, you've got two plots of the Pacific and the Atlantic. And you'll notice as you move to the right, the sort of red bit in the northern and sorry about that. As you move to the right, you'll see the red area at the top and the bottom is getting smaller, and the blue area in the middle, that's the equator regions, is getting bigger. That means there is less cloud cover. Clouds, low-level clouds, reflect radiation. So these are recent papers that have come out. So the situation is really quite complicated. Why are we losing so much cloud cover? And also, obviously, we have greenhouse gases, and we're talking about 0.3 watts per meter squared per decade, and about 3.7 is the equivalent of double CO2. So there's quite a lot of significant meteorological effects. And so we are now looking at the topic of marine cloud brightening. I've given you an introduction and to say, look, the planet is changing. We have to appreciate it, and then we have to decide what to do. And one of the ideas that I was involved with, and it's only since about 2000, is marine cloud brightening. So the argument is if you increase the number of droplets in the clouds, low-level clouds, you'll make the planet brighter, reflect more solar radiation. So that's the next section. And the second point there is that something called coded modulation. That's a really quite difficult idea, that maybe if we seed in certain areas, it has impact in certain other areas. So this is a way of suggesting, if we do this, we need to do the research first. If we do it, then can we modulate, can we control the side effects, and how will it affect things like precipitation? So here we have the standard plot of what we need to do. In my opinion, we are going to have to consider solar radiation management. So if you look at the sun, it's approximately 1,360 watts per meter squared overhead, which works out about 340 watts per meter squared over the whole day and night. However, a mean of 70 watts per meter squared is reflected back. So we're going to have to, I think, consider how we cope with the fact that we've got a warming surface. It becomes very complicated because upper level clouds, well, let's work from the top. The one idea, as Mr. Musk's idea, is that we have reflectors in space. These are very expensive. The next idea is, which we'll talk about, is stratospheric aerosol, like volcanoes. And our idea is to just increase slightly the number of droplets in these low-level clouds. So here we go. This is marine cloud brightening. It really comes back to the 90s or 2000s. And a man called Toomey, an American scientist, suggested that, in fact, the number of droplets in the cloud controls the amount of reflected radiation. And then a paper by Latham wrote that this could be used if the planet gets too warm. And this slide here shows the stratocumulus clouds over to the west of, in the Pacific, to the west of Arica, the west of Chile. And on the right-hand side, you have a sample of glass beads. Now, this was produced by Stephen Salter. And if you look at those two jars, they contain the same volume of glass. The jar on the right looks whiter, and it is whiter. It's got a higher albedo reflectance, And all it is the fact that the glass beads on the right-hand side are smaller than the glass beads on the left-hand side. And this is one of the purposes of the experiment in 2008 of Chile and Peru, was on the left-hand side, was to look at these clouds, to understand them. And we have suggested that we can say seawater, salt crystals, there's other things you can use, but seawater was obvious, that into these clouds just to increase the number of droplets. The system can be shut down within 2 or 3 weeks, unlike stratospheric aerosol, and you can precisely do it. So this is the background for marine cloud brightening. And we did some modeling, we did some initial modeling on this, and this is the details of the model. I really don't want to spend any time looking at it, but if you look at this talk later, you can find out the details of the model we used. So this plot here now shows you what we did. We took the model, and it's a Mercator projection, and we chose the 3 most popular regions for stratocumulus, which is between about 3 and 5% of the ocean surface. And we increased the number of droplets in the stratocumulus clouds. Now, stratocumulus clouds are very important. They don't rain, so they stay there for days or weeks. So the first experiment was we increased the number of droplets in that area. The second experiment, we did it all over the globe. And these were the experiments we conducted. And when you look now at the results of this major plot shows the effects on the energy balance. So this is the change in watts per meter squared in the plant. So as a rough guide, 3.7 watts per meter squared is the equivalent of double CO2. I call it double CO2, but there's methane contributions, there's all sorts of other gas contributions. But double CO2, and you can see that it produced in certain areas, it produced a 40 watts per meter squared cooling, but generally over all the maritime regions, it produced a cooling effect. And the first paper that Latham did was in 2008, which I was involved with and produced these plots. And in 2012, it was a sort of second paper. And what was actually done, if you look on the right-hand side, we assumed that we increased CO2 as a proxy for greenhouse gas warming. It could have been, we could have chosen anything, but it was a radiative effect. And then we let it go flat for maybe 30 or 40 years. And then we took measurements when we assumed the atmosphere was in its new equilibrium. And this bottom plot shows you exactly what we did. So there's other suggestions. I'm not going to talk about it, but Danny Rosenfeld and group basically said, if you seeded over the whole planet, that's clear air brightening, then I don't want you to read this, but you can actually, he argued that that's what we should be doing, spraying these things into the clouds, into the clear air, over the sea. Over the land, it won't make any difference. So now let's just get on to some results here. This is really, really quite difficult to understand. So I'm just going to focus on the right-hand side. So if you take a climate model, they're all really not very good on precipitation. So if you look at the top left-hand plot, A, the discrepancies between the control model and the observations, about 0.4 millimeters a day. That is a lot. That's a lot. So we know the data and the model don't agree, and people argue about how good the data is, and I know the model isn't very good. The plot on the second plot, which is B, was what happens when we increase CO2 from 440 to 560 parts per million. And that produces an increase of precipitation of about 0.04 millimeters a day. And that is within the right ballpark of what we would expect. what was done originally. And the final plot at the bottom here is see the differences between a geoengineered, what I call geoengineered 2CO2 solution with a marine cloud brightening in 3 regions. And there is an increase a little bit more in precipitation, but over the whole globe, then it really is, you cannot say there's any difference between 0.04 millimeters a day and 0.07 millimeters a day, especially when you'll consider that the models are in error by so much. So there are differences, and I'm going to come back to that in a minute. But before I leave this topic, I just want to show you that the first of all is the effect on the poleward heat fluxes. Now, this is important because it reflects how much the poles melt. So we start at the equator, and basically the reason these are always plotted this way, we will start from the equator, so that by the time you get to the right-hand side, you've got the difference, a total difference in radiative balance between one side and the other side. And if you look at the first of all, the bottom curve here, this is what Danny Rosenfeld seeding the whole atmosphere. And if you did that, you're going to have the ice age return, essentially, if it worked. If you have the double CO2, that's the top curve. And now it doesn't look much there. That difference between the top curve and those other curves doesn't look much, but it is, because we're talking about petawatts of energy, huge amounts of energy. And if you look at the middle red and blue curve, there's very little to distinguish, but that's the difference between between now and double CO2 and marine cloud brightening. So we're arguing the models suggest that it'd be a sticky plaster. It will not solve the problem, but it will address temporarily the problem. And here we've got the sea surface temperatures. This focuses here. The black squares are the coral reef agents. 3 seeded area seeding. You can see it reduces the temperatures by 2 degrees. And this is important. A couple of papers there to refer it. So the model suggested, yes, it would. Of course, in the North Atlantic and the South Atlantic, it's still a little bit warmer, but in the middle, the important subtropics, it's cooler. And if you look at the next slide, this focuses on specific regions, and UAE is just off to the right there, but you can see that it reflects the fact that this is focusing on the hurricane region there. And obviously in the US, they're worried about the increase in hurricanes. And if you go to the Pacific, you've got the increase in typhoons. There's a corresponding plot. I haven't shown it here. And you can see that it's cooling those major regions there by significantly, by order of 1 degree Celsius. And so the model is suggesting that it will have a desired effect. So this was work done maybe 10 years ago. A lot of other people have done more work. But what I'm suggesting now is what is going to be, I think, the novel, completely novel part of this. So the coded modulation. Now, this is really quite complex, and I don't really want you to spend any time unless you look at it afterwards. Essentially, we're going to divide the oceans into a set of areas. We chose 89. And the idea is that you can seed in these different areas, and what effect does it have on the planet? Now, we focused initially on precipitation, and I'm arguing that we need to do this again. So the first point is coded modulation is complex. The second one is the first paper that ever actually did coded modulation, although they didn't do it in such, is Jones 2009. I'm going to show you in the next slide. And Latham 2012, this was the second paper. And we defined the algorithm in 2013. So the whole point of this talk is to try and persuade people to look at this and how we might get a better handle on this. So here we've got the paper of 2009. Now you'll notice that there's 3 areas here. These areas are very similar to what we used in 2008 and 2012. So we've got the 3 areas of seeding. What effect did it have on rainfall? It had effect on other things, but I'm just showing you the effect on rainfall of seeding in the initial areas. Now, Latham and I and Salter didn't isolate the different areas. This paper did. So if you look at the area B, which is NP, so that's called the North Pacific seeding area, you'll notice that there are effects in the green effects in Australia and in the Amazon and other effects. That's quite big. I mean, the scale isn't really satisfactory, but it's really quite big. And the reason we chose the scale, or they chose the scale, is because if you look at the bottom here, so at the South Atlantic seeding area, that area, you can see that if you seeded in that area, in the northern Amazon district, you would get a huge change in precipitation of up to, if you believe the model, 0.8 millimeters a day. That is a lot. And you would also get some effect in Africa. I'm afraid there's not much effect that's noticeable on this color scheme for the UAE, but there's a huge effect. And if you look at the South Pacific region, which is the bottom right, that's this curve here, this area here. If you look at that region, you will see, sorry, I've taken it on the slide. If you look at that region there, you can see that there's increased precipitation in southern Amazon and not much elsewhere. So in this study, the biggest effect on precipitation was in the South Atlantic, the SA region. So this was a simple experiment. They divided the 3 areas we'd chosen. And now this is the really complicated slide. And really, I just want to give you a flavor. Ben Parks was my student, and we worked with Stephen Salter and myself, and he did this plot. Now, this plot, and I'm going to emphasize it in the next slide, gives at the bottom right here, it shows that in a certain region we chose, which was this your area, that if you seeded in certain areas, the rainfall would increase in your region. If you seeded in other areas, the rainfall would decrease. That is about 0 there. And so seeding in certain areas, the smaller the standard deviation, which is there, the better we feel, and the bigger the standard deviation, well, the more the errors. So what do? We had 89 areas here. You can see them in different colors. I've tried to isolate them and show them what we did. And we turned on the seeding on and off in a random way. So essentially, we're getting some mechanical device and switching the seeding on for 2 weeks at a time. 2 weeks we thought was, well, I thought was a good time to choose. So upper right diagram, 89 areas. And then we seed it by 2/3 and 3/2, 10 to 14 days. We took the average, we removed the seasonal average, we subtracted to produce a new 0. You don't need to know any of this detail, and we did it 8 times. And then we looked at the results, and we produced this transfer, what we call a transfer function. This scheme was created by a man called George Mackay, who was David Mackay, who was a scientist in the UK, an international scientist, and he proposed this was a mechanical sort of test. And so what I've done again on this slide is I've enlarged the picture on the bottom right. So here we're looking at what I call the Arabian region, which includes UAE and Oman and that sort of region of the globe. So we're talking about the region around there. And we said, look, what affects the precipitation over the ground, over land, the most? And we found that if you sprayed in certain areas, you could get an increase in precipitation and exactly the same plot as before. And this, if you see it in these areas, you'd probably reduce. The zero is in the middle. The zero is across there. So this corresponds to an increase in precipitation globally, which is consistent. You put more water into the atmosphere, you're going to get more rain out if it's in balance. So it does, but certain areas would do it. And what we've done here, that we found that if you sprayed in certain areas, and this is not for the Arabian region, that's the 11 plots here, on these 8 plots here, we specifically looked at some of the regions. So, for example, let's have a look at one that's most significant. So it's the 3rd plot down. If you seeded in those black regions there, you had a big effect on the rainfall in the Amazon. Now, it might not look; those colors might not look very significant, but that is a big effect. If you did it there, you would get a little bit of effect. If you did it there, you get more effect. And of course, if you did it in the Northern Hemisphere, you would get effects in different parts of the world. So if you did it those parts in the Northern Hemisphere, you had an effect in Australia. So it's what the idea of teleconnections. So I'm coming near to the end of the talk, but this is a plot for specifically looking at the Northern Amazon and the Southern Amazon. And this is what I was trying to get over to you with this plot here, this plot on the right-hand side. So we randomly chose, it was only a PhD, what happens, how do you control what happens in the rainfall in those regions? And we found that on the right-hand plot, you'll see that certain regions actually reduce the rainfall, and these red regions increase the rainfall. On the left-hand side, we did the Southern Amazon, and you found that really for the Southern Amazon, most regions would enhance the rainfall. Now, we haven't done anything much for this region here, and I hate to say that all the models suggest that in the double CO2 atmosphere, there won't be significant changes in the precipitation. However, these models are pretty poor when it comes to precipitation, even numerical weather prediction models. And so this again is what I'm trying to emphasize, that by applying this coded modulation into those regions there, and I've only shown some of the regions, you can affect the precipitation. The other point is there's going to be effects on precipitation. There will be and other things, of course, temperatures will rise. So let me just sort of summarize, because it's coming up to my 30 minutes now, that the specific objectives of this presentation are to, first of all, to talk about marine cloud brightening. Now, we were all at a weather modification, 11 years, we haven't had a weather modification conference for the World Met Office, and they had one this year in India. And people were talking about increasing precipitation, and this, I would argue, is the most important weather modification for the planet, not in different regions. And because the planet is warming up for a multitude of reasons that we really don't fully understand, but obviously greenhouse gases of all kinds are one of them. Changing cloud cover is another. 8,000 years ago, there was the Younger Dryas event where the temperatures dropped globally by 8 degrees and then came back. So the system does make changes, but this one is going through now is very rapid. It might not seem so. Mankind doesn't often have a chance to respond to rapid change. It's never had to. So what are we now saying in section 2 is that we really do need a plan B. And plan B is going to be that we're going to have to reduce solar radiation input. And the water vapor is now the dominant, I would argue, the dominant. So I've been writing to UK ministers and other people saying, look, this is what some scientists call the runaway greenhouse effect. And if you look at Mars, they used to have lots of water. You look at Venus. And the argument is that marine cloud brightening, there's other ways of achieving it, and there's other things we can do in the oceans. But if we just look at this one technique, and I'm just emphasizing this is one technique, that we can do coded modulation and will tell us which regions are safe to do it. And the point is that I'm really asking for scientists to do this. I really need some scientists. So I went to India. Some people in China are interested in doing this, some people in India. And the emphasis is that we're going to have to do some modification. Now, obviously, people are interested in increasing rainfall in different parts of the world or decreasing it. But I would say this is the next stage on. And the application of this coded modulation algorithm can provide information on this. It can discuss it. Some people around the world are now considering this. I think we have to look at, I'm very cautious about sulfur aerosol injection, SAI, stratospheric sulfur injection, because of the side effects it's going to affect. The ozone hole, it's not necessarily going to cool the poles too much, and it's going to affect crop production. So I'm suggesting that as scientists, we need to discuss the idea of marine cloud brightening and the other ideas. So 2 minutes too long, but thank you very much for listening. And and then please ask me your questions. I've got 4 questions already asked here, but I will wait to see if we should start. I should start answering those, or if there's any other questions. So over to you, Amir. Right. Any questions? Right. Okay. So I've had no questions from the floor. So I've got 5 questions already sent in, and I'm going to first of all talk about what are the advantages of marine cloud brightening compared with the other methods. So can I go back to the slides, please, again? Because I'll go back to the slides and I'll show, I've got some extra slides here. And this one is a slide that was produced after the Mount Pinatubo eruption. And you can see that the plot underneath is temperature. So you can see this eruption occurred approximately in 1991. And by 1995, the planet returned to its previous state of mean temperature-wise. And this is probably the main contender for solar radiation management. However, you obviously can't control volcanoes. The idea is that you perhaps fly with aircraft or some other way, or use existing aircraft to put crystals into the stratosphere, above the troposphere, above the weather. Now, this is a way, yes. This, unfortunately, because you put it in the stratosphere, you want it in the stratosphere to reflect the solar radiation, but it's long-lasting. It's long-lasting. And being long-lasting, if there are any side effects, you can't turn it off. So there's been many papers. I'll just show you some papers. Just a minute. Oh no, I've not got the papers here. But there's been many papers on the topic. Suzanne Tilms has done some papers, and that it will affect the ozone hole. So the ozone hole, it will increase the size of the ozone hole. It will affect, a recent paper has come out in 2025 saying it will reduce agricultural production. So we already have the effect, if you're in South America, towards the southern hemisphere, that road workers were actually exposed in Chile and Argentina to lots of solar radiation. And in recent years, they've been getting cancers. And the cancers are due to the fact that the ozone hole has reduced the amount of ultraviolet. So this is definitely a method that you could use. And you could use the same techniques we've done modeling. But the problem with stratospheric sulfur is as soon as you put it up there, it then whisks around the upper atmosphere for years. And you couldn't use the coded modulation. So I'm cautious about this. There are other techniques that are possible. People talk about growth of seaweed. We've reduced seaweed by 80%. Obviously, it's a food source as well. People talked about bubbles to protect the coral reefs, and that would certainly cool the ocean down. So the advantage to me is that you can switch it on and off, and you can control it. And if you don't like the side effects, switch it off. You can move the vessels around. In the 2009 Royal Society report, they mistakenly got the cost of marine cloud brightening wrong. And we calculate that it would cost about $4 billion a year to institute this, which in terms of the global economy is not worth thinking about in terms of the cost. And obviously Stephen Salter designed ships, but the idea is that we could do it. The major problem is obviously working out where to do it and getting the correct size, and people are looking at now. So the second question was, how does the coded modulation help minimize unintended consequences? Now, it essentially doesn't help minimize unintended consequences. What it does, it defines what the consequences are. What are the impacts? So if you're in that region of southern Amazon, and someone said, oh, we'll see it in the South Atlantic, you would realize from the results that southern Amazon is going to have a significant reduction in rainfall. So what it can do is this technique is, as Jones did it in 2009 with just 3 regions, you can analyze where the impact is most. And if you believe Danny Rosenfeld, clear air brightening, spraying all over the sea, which obviously would cost probably $10 billion all over the year, then it would cool the whole planet, and we haven't done the rainfall calculations for that. So there are going to be unintended consequences, but the coded modulation will help it. Now, there's many people who say that the climate models are inadequate, which I would totally agree with, and that you need 1 kilometer resolution. Now, the results I've shown were 100 kilometers resolution. That's between the grid points. And the amount of computing required is vast. So the advantage of this is you can do a marine cloud brightening in a region, wherever, and you could see if it worked. You could put a lot of aircraft satellites, and then you could then discuss, should we start implementing it? So the problem then is, which comes on to the third question, what are the next steps? And the next steps are that we really need to model. Now, in the UK, they're making spray mechanisms. Now, different groups have different ideas. I've seen an example where the spray mechanism actually produces the right size. The right size is critically important. Make them too bigger droplet sea salt crystals, then the clouds will disintegrate and precipitate out. Daniel Harrison in Southeast Australia, he's got another way of making the sprays, and he says it's too expensive. I don't think it is, because I've seen devices that can do it. Technologically, it's not that difficult. And that was part of the UK ARIA campaign. And several different groups of people around the world are looking at creating the right sizes. So, so really, to answer the third question, what are the next steps? Then I think you've got to do the engineering, and you've got to do some more modeling. And I'll show you what I mean on this next slide here, that this is what we did, simple modeling, and we sprayed. And what it is, these plots are of droplet sizes, and you really want lots of green sizes because they're small. There's the small droplets, and the and the big ones are represented by the well, as you increase, you get different sizes. So you start, green is less than 10 microns, and yellow is bigger than 50 microns, red and yellow. Now you don't want the big ones, you want the little ones. So this is some simple modeling. It needs to be done in a more way that you can, on the small level models, this is 20-meter resolution models. So you've got to somehow combine, this is the next question, the challenge is these low-level climate models are not good enough. And you're going to have a mixture of low-level ones and high-level models like this one here. So this is what needs to do this study, but you've also, at the same time and in parallel, I think you've got to do the coded modulation. And this is these are the slides that this is to do with global temperature. But that is the other question people asked. Well, aren't you pumping a lot of salt into the air? The previous question, and I would say no. The normal amount of salt you get pumped into the air by the sea is 5.4 gigatons, which is a lot. And in our method, even if we had 2,000 ships, boats, whatever, we'd produce 0.033 gigatons. So the effect is so small, it's in the noise of the standard deviation. So yes, this is I think the two major ideas are stratospheric sulfur, which I think the Russians will probably do very shortly, talking to them, and marine cloud. I think marine cloud brightening. And of course, I'm biased because I'm a cloud physicist and an atmospheric modeler. So this is what I've done work into. And the final question, to take us up to the 45 minutes, the question is, what is the role of water vapor? Now, I'm going to come back to this slide here. And this is my second sort of bugbear that I can't get people to appreciate. I'm just going back to the relevant slide here, which talks about water vapor. And the slide basically comes back to the complications. So I've talked about marine cloud brightening, I've talked about solar radiation management, but what is the underlying problem? I think the underlying problem is greenhouse gases, and that includes methane, CFCs, all those things we've pumped into the atmosphere. But the bigger problem now is that the surface of the sea is getting warmer. And when it gets to 2 or 3 degrees, what actually happens is that as the sea gets warmer, the saturated vapor pressure of the air increases. There's more water in it. And therefore, there's more water to fall out, but there's more absorption. And it's intriguing because this, for me, I like to drink a cup of tea. And if I go up to the Rockies at 3,000 meters, I can't make a decent cup of tea because the water boils at 90 degrees Celsius. So the amount of water vapor in the atmosphere controls the temperature balance. So if you go to high mountain plateaus, I don't know, 3,000 or 4,000 meters up in the Spanish plateaus or in the Hajar Mountains or wherever, then at night it gets cold because there's no water vapor. And during the day, it gets very hot. Now, if you increase the water vapor, as you do in the subtropics, you get high humidity, and then the temperatures don't drop at night. So we see classic examples. We see it in other planets. So what I'm trying to say, to elaborate on this idea, that it's a concept that some meteorologists have realized. The Earth is in this sweet spot. And if for some reason the sun got brighter or whatever, and the planet warms up, then with increased solar radiation, the water vapor is going to increase. And we're not going to get to the situation like Venus, which receives about the same amount of solar radiation we do at the surface, where the surface temperature is about, I don't know, 400, 500 degrees Celsius because of the greenhouse effect of CO2 and sulfuric acid. We're at the moment in this sweet spot, and it comes down. The reason is, and you're going to have to go away and look at this to answer this question properly, is this paper by Schmidt, who analyzed what the contributions were. And CO2, yeah, 19 to 24%, but water vapor was 50%. You've got methane, which is 10% or 8%. You've got ozone and you've got CFC. So I talk about CO2 as a combination of CO2 ozone. So to answer this last question, which is slightly longer than I've gone on, 45 minutes, but the feedback is critical. And I'm spending a lot of my time trying to persuade people it's not just CO2. And as Lovelock said, recycling is to solve the middle class consciousness of they're doing something. The bigger problem now is the water vapor. Okay, it's a feedback. I agree it's a feedback, but it's the biggest forcing function, the increase in water vapor. So those are the 5 questions. I've now got an extra question, which has just come through the chat. So I'm just going to, there's a question regarding how MCB is an artificial near-surface atmospheric sea spray comparable to natural smoke in the world due to wind and water. How is artificial seeding of the near-surface atmosphere with sea spray supply going to affect the world ocean? And how will it interact with the water, the wind, water in reaction? And that's very interesting question, because if you looked at the previous results, if you can get a copy of the PDF here, you'll see that the first experiment in 2008, we did with an atmosphere only model. And the 2012, which was the same as the 2009 by Jones, we did it with a model that has interaction between the ocean circulations and the atmosphere. So when you cool the areas of Namibia, South Atlantic, South Pacific, North Pacific, what actually happens is that the ocean currents, the Atlantic meridional overturning circulation, the polar, southern hemisphere subpolar vortex, will take the water away. And the effects, it will have an effect on the El Nino. The classic strong El Nino will disappear. So the salt we produce itself from the ocean is going to have minimal effect on the salt deposition, if that's what the question's about. But the wind-water interaction means that although we seed in just a few areas, the oceans transfer this cooler water to other regions. And that's why it's so effective on cooling the globe. You can ask, well, they're just seeding small areas. How does that affect the melting of the polar ice caps? And the answer is simple, that if you control the flow of heat from the equator to the pole, that is what is melting the ice caps. It's their flow of heat, temperature, and moisture from the equator to the pole that's melting it. So by cooling the subtropics, even in those small regions, you're cooling the whole planet, in fact. So the aerosol is coming, and that's where Danny Rosenfeld's comment was, spray it all over the oceans. A lot of it will be ineffective because the amount we're spraying is minimal compared with a subtropical storm or whatever we're putting in. But on the areas of the subtropics, the doldrums, or whatever area you might want to call it, that will reflect solar radiation. And it's reflecting solar radiation in the subtropics that will do most to stop the poles heating. And of course, for the UAE, you'll be getting temperatures of 50 degrees Celsius, not just you, but in that subtropical band in dry areas. It will do a lot to cool the temperatures there. But again, that's slightly different from talking about precipitation. But we need, the temperatures are easier, precipitation is more difficult. But I think all the areas, especially in the subtropics and equator regions, are going to have to consider the changes in precipitation. I hope that answers the question. Are there any more questions? Well, thank you very much for listening. I hope I've given you some information. Please contact me or UAE rep to get a copy of the presentation. I'm happy to talk about it. I'll be even more happy to talk about to anyone who wants to help us do this modeling, because it's not very difficult, but brilliant for postdoc, brilliant for young scientists. So I'm making a plea, I suppose. Thank you for listening, and I hope I provided you with some useful information. Thank you.